Okay, welcome. Thanks for coming. And so this is I'm so glad that the storm is over because there was a lot of internet and power outages the last few days. And but everything looks good right now, so no problem. And I just got back. I'm still a little sweaty from skiing here, so it's that happens. So let me tell you the plan today. So the first thing, as usual, is we will look at questions. So I'll answer any questions that you might have. And that could be about anything about statistics. Could be about something we've done recently. It could be the project or whatever it might be. Happy to answer any questions you have. And then after that, we're going to get into the chi-square distribution. So that's a new one. We haven't had that one yet. It turns out the mathematics of that is actually really brutal. So the good news is you don't have to worry about it. All you have to do is use a calculator. So, but if you want to learn the math, you need to take a lot of math classes. It's just a heads up. But we're going to get into the chi-square distribution. And the main thing is it is going to allow us to do statistics on a type of survey question with data collected that we haven't done yet because we haven't known how. So what kind of data or what kind of variable have we not dealt with yet? Any of you know? Yeah, the qualitative not yes no variable. So we qualitative yes no we dealt with, but if it is something that's not a yes no question, like what month were you born in? That's definitely not a yes no question. For me, it's July, and you don't write that as a number. It's just a month. Okay, or what's your favorite color is another one that pretty hard to write as a number unless you're a physicist. But the point is, we're going to be dealing with a lot of different survey questions where it's not necessarily, or it's not a quantitative data, and it doesn't give you a yes no answer. And that's what this chi-square distribution and this chapter 11 is all about. It turns out we're going to be able to, we're going to do 3 different hypothesis test types for this section. They all use the chi-square distribution. And the first is a chi-squared goodness of fit test. I don't expect any of these to mean anything to you right now, but hopefully you'll pretty much understand it by the end of this webinar, which may not go as long as usual. We'll see. All depends on how long you want it to take. Then we'll get into the chi-square test for independence. So we've kind of talked about the assumption sometimes that the variables are independent. So now we'll talk about one way of finding that out. And then finally, we'll look at the chi-square test for homogeneity. And that is another chi-square test. And all these typically are used for when there's a qualitative variable. Okay, there are some cases where you can do with quantitative when you have brackets, because then you would say first bracket, second bracket, third bracket. And that can be considered qualitative, even if the survey question sounds quantitative. So that is the plan. Just to let you know, I always like to remind you of things that are coming. So one thing is an odd week. So that means that you don't have to worry about an exam. But what you should be really focusing on right now, what's the big thing coming up in a few weeks? Yeah, project 2. Project 2. Okay. Chi-square test for independence. Yeah, you were looking for you were using that to decide if two answers to 2 different survey questions specifically are independent. And that's different than a chi-squared test for independence, where it's not focusing on this answer and this answer. It's all possible answers to the first question versus all possible answers to the second question. And it turns out, which we're not going to do in this class, but the mathematics to get the test statistic turns out to use what we did in probability, but it's a lot of work to do that. It can be really tedious. So I tend to kind of throw that under the carpet and let the calculator do it. I mean, I coded the calculator, but now I just let it do it. It's a lot easier. So project two is coming up not too long from now. So just to let you know, we're in week 9 and it is due at the end of week 11. So you have like more than 2.5 weeks, but it's the kind of thing with these projects, you want to have a timeline so that you get it set already. Yeah, I recommend having your proposal submitted this week already. You're ready to do everything you need to do with the project in terms of knowledge, because the project goes up to chapter 10. And today we're talking about chapter 11. So that's the good news, is that you are ready. So definitely make sure that you have a project that can work by posting on the project to discussion board. And then once once I've said, yeah, that one can work, then get your data. And again, unlike project 1, the data sometimes is really quick to get. Okay, because it doesn't have to be a survey of people. It can just be, looking at temperatures or prices or, whatever, going online and looking at heights of players or something, that type of thing, age of the actors, or whatever it might be. But you can just quickly, find that. You don't have to actually like go and talk to people. Okay, you're allowed to, but you don't have to. You don't get more points if you talk to people. I do want to mention something because it's been a big problem with people who have proposed their project. It's one of the big issues, and that is the population size must be bigger than you could handle if you tried to survey or if you tried to find all of the data. So if the population size is under 100, then it doesn't work for project 2. And no, I'm saying population size, not sample size. Because if the population size is under 100, you could just do the whole population. You don't need a confidence interval. You don't need a hypothesis test. You know exactly what the population mean is. Does that make sense? So it definitely needs to be something where it's a large population size. Okay, maybe in the millions, Hopefully that makes sense. Okay, I want to mention something, and this is knowing how to read a letter. Sounds easy, doesn't it? So it turns out that this is all about the chi-squared distribution, and that is a letter. The Greek letter chi is a letter. Okay, squared means multiply by itself, and then it becomes a square, just like 5 squared is 25. So chi is a number, it's a letter that's a variable that stands for a number, and chi-squared is the number squared. And it is this guy right here. It kind of looks like an X, but it isn't. How is it a little different from the letter X in terms of shape? What do you notice? That's the whole thing, that's the only variable basically we're going to have that we haven't learned yet in this class. So how does it differ in terms of shape? Fancy line. Yeah, the key is it's not a line, actually. It's a curve. So it's curved here. Okay, so the one that goes from left to right is actually a little bit curved. Okay, and that makes it a chi. And it's a capital letter, and it's Greek. I've never had a student that is fluent in, comes from Greece and is completely fluent. One of these years, but it's been decades. So maybe someday, they'll be able to know everything about the Greek alphabet. I only know it mathematically. Okay, so what we want to do is we want to look at this chi-squared distribution. I figured I'd just show you a little bit what it looks like. By the way, if I go to links to calculators and I go to interactive statistics, so that button there, I can actually find a whole lot more stuff. And there's a visualize the chi-squared distribution. And does it look normal? Yeah, it doesn't look normal. In fact, how would you describe this distribution in terms of the words we've already had, maybe in chapter 2? Do you remember? Yeah, you say right-tailed or skewed right. It's unimodal. Another thing to notice is that it stops at 0. It never becomes negative. Any guess on why it doesn't become negative? Yeah, squared. Take a number, square it. You're not going to get a negative number. If you take a real number and square it, you can't get negative. So the good news for y'all is that we don't have to worry about a left tail or right tail in a two-tailed test because the chi-square only has a right tail. Is that clear? And it turns out there's degrees of freedom depending on how many characteristics there are. And if you change the degrees of freedom, it changes the distribution a bit. And if it's a lot, it starts getting closer to being a little like normal, but it's not exactly normal because it always stops at 0. Normal never stops. Okay, so that's the chi-square distribution. And again, the last thing I'm going to do is try to explain it mathematically and give you equations. And there is no nice equation. It's brutal. So stop there. Sound good? So that's the chi-square distribution, and that's a picture. And notice that, like, say, on this particular graph, at 14, if I look at the probability of being greater than 14, that'll be the area to the right. Okay, I don't expect any of you to be able to do this one, exactly by hand or anything like that, but I want you to at least picture it. And what do we call that? If the test statistic were 14 and the area to the right would be this is a biggie in hypothesis testing. It's the biggie. The rejection region, not quite. The p-value. The p-value. It turns out the rejection region is the area to the right is whatever that percent, like a 5% level of significance. And that region with the 5% level of significance where the area is 0.05, that would be the rejection region. But if you have a test statistic of 14, the area to the right of that would be the p-value. So that's what's happening in terms of the picture. Okay. And again, I'm not going to get into any of the mathematics behind any of this stuff because it's too hard. Okay, so that's the chi-square distribution. And now let's do examples. Okay, so here's an example. So in California, okay, by the way, I looked this one up yesterday. So this, you can quote me on this one. 40% of residents are Latino, 35% are white, 15% are Asian or Pacific Islander, and 10% are other races. Okay, not sure if you realize that that's how California is now. It's not, white is not the most common anymore. Now it's Latino, and that's California. Okay. Okay, so a question you might ask is, let's look at California community college students. Because one of the things you want, let's say you were, the chancellor of California Community College, you want to make sure that you're serving the students and you're not having any kind of racial bias. Does that make sense? So the question is the distribution of races different for California community colleges? All right. So first thing I want to ask you, what would the survey question be? What would we ask this California community college student? Always important to be able to read this and know what the survey. Yeah. What is your race? Okay. And the person is not going to say 74. The person is not going to say yes. Right? The person is going to say, I am Latino or I am Asian or whatever their race might be. Does that make sense? It's going to be a word answer. It's not yes, no. It's not a number. So this does not fit anything from chapters 1 through 10. So we're in a new area now. Any questions on kind of identifying this as not fitting into 1 through 10? Okay, or maybe I should say really 8 through 10, because that's when we started confidence intervals and hypothesis testing. Any questions on that idea? Okay, now, and these numbers I made up because, but you can imagine a survey was done of 300 California community college students, and 125 were Latino, 92 were white, 33 were Asian or Pacific Islander, and 50 were other races. Okay. So what can be concluded at the 5% level of significance? Any questions on the example and what the question's asking about? Any questions? Okay, so in terms of the process, it's still hypothesis testing, so it's still going to be the same step-by-step process, but each of the steps is going to look a bit different than what we've seen before. So step one, hopefully you're used to, is to write down the null hypothesis and the alternative hypothesis. Is that clear? Okay, so we're used to doing that. And in the past, what I told you is you had to do it in symbols, right? It turns out symbols are much messier when you're dealing with this chi-squared stuff. So it's probably better, strongly recommend not using symbols when you're dealing with anything in chapter 11. When we're dealing with chi-squared tests, we're going to be doing words. And the H naught in this case is the distribution of races at California Community College is the same as the distribution of races in California. Okay, and we know the exact distribution in California. That one I was going to quickly look up. We want to find out if it's the same in California community colleges. Okay, H1, remember it's like a kind of a debate. H naught is a status quo, what the other guy's trying to say, and you're saying, no, 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 I don't agree with you. So the opposite of H naught is the distribution of races at California community colleges is not the same as the distribution of races in California. Any questions? Any questions at all on H naught and H1? Do you notice anything highlighted? Notice anything highlighted in H naught and H1? Yeah, distribution, not distributions, distribution. So I want to focus on that because on a different test we do is going to be distributions with the plural. This is going to be a single distribution. Okay. So, and hopefully you're used to it by now. If I highlight something and mention it 3 times like I did, distribution is highlighted, distribution is highlighted, distribution is highlighted. What does that mean? Yeah, it's important. And if you don't put it on your exam and on your discussion post reply, then you're going to lose points. So no reason to lose points. I'm telling you now. So it's important that you listen to the webinar. Those who are listening are listening. It's the ones that aren't. That's the hard part. I can't force everyone to pay attention, but I can plead. So make sure that you put that it's always going to have that word distribution for this type of test. Okay, now it turns out what we're looking at is we have a known distribution, and that's California as a state. Okay, distribution of races in California. We know the population distribution. And we have an unknown distribution, and that's California community college students. Okay, that's the unknown distribution. We only have a sample for that. When you have a known distribution and you have a sample, and you want to find out if the sample's distribution is the same as the known distribution, the test we're going to use is goodness of fit. And the reason they call it that is we want to see if the distribution of, in this case, California Community College students fits the distribution in California. Is it a good fit? So that's why it's called the goodness of fit test. And by the way, I didn't make this up. I'm using what everyone in the country uses. Probably anyone who speaks English uses goodness of fit test. That's the name they call it. Any questions on the example so far? Okay, so now what I'm going to do is I'm going to create my observed and expected table. Okay, that's always is a very step-by-step process when you goodness of fit. Step one is to read the question. Step two is to write down the null hypothesis and the alternative hypothesis. Step three is to look at it and see if it's a goodness of fit test. If it is, write down the word goodness of fit. The next step is to write down the observed and expected table, is what we call it. So what we're going to do is we're going to write down for the columns will contain each of the possible answers. In this case, the possible answers for this question, a person could be Latino, white, Asian Pacific Islander, or other. And then the rows will be O and E. Any guess on what O stands for? This is O and not 0, by the way. What does O stand for? I've said it, but you may not have been like completely paying attention. Yeah, O stands for observed. How about E? What does that stand for? E stands for expected. So the observed is what we observed in our sample. And for this example, it's really easy. How many Latinos were observed? No, we didn't observe 40%. Yeah, 125 Latinos were observed, right? That was the observed. Observed is in the sample. The 40% is not the sample. The 125 comes from the sample. 125. How many observed whites were there? Not a trick question. Should be obvious. Yeah, that's 92. And then the Asian Pacific Islanders are 33. And the others were 50. Any questions on that? Okay, then we have the expected. Okay, to find the expected, we expect, and when they say expected, we say, what would we expect had it been exactly what the known population was? The known population has 40% Latinos. That's California. So if the community college system had exactly 40% Latino residents, and we observed exactly what we would expect, then how many would we expect? Well, it'd be 40% of 300. And you can quickly do the math. I could do this one in my head, but 0.4, that's 40% times 300. And by the way, 4 times 3 is 12, so it's 120. Any questions on that? And that's the expected number of Latinos. Okay, similarly for whites, we're going to take 0.35 times 120. And how much is that? Yep, 42. Sorry, not times 120. I made a mistake. Times 300. My error. 0.35 times 300. That's our sample size. Sorry about that typo. So 0.35 times 300, because we had 300 students, we would expect 35% to be white. 0.35 times 300 is 105. That's the expected for whites. We have the Asian Pacific Islanders, and that was 15%, 0.15 times 300. And that was 45. And then finally, we have 50 from other races. So that's going to be 0. And the other races were 10%. 1 times 300. And that is 30. Any questions on that? Okay, you might notice, are any of these expected any of the observed what we expected them to be? None of them are what we expected them to be. Does that mean we can say that the distribution of races in California community colleges is different than in California? Because none of the observed are the same as the expected, so they're different. What do you think? Can we say that the distribution is different? And the answer is no. Yeah, the answer is no. And the reason is we have a survey of 300 California community college students. We didn't look at them all. There's like 1 million or so California community college students. Okay, I don't know if you realize there's a lot of California community college students. All we did is look at 300 of them. So hopefully you're used to that from statistics. If you only look at a sample, you cannot say that knowing the sample, you exactly know what the population is. What we can do is we can find the p-value. And what that basically says is that if the distribution had been the same, and we did another study of 300 California community college students, then it would be the probability that the observed values would be as far from the expected values as what we saw. Do you see how that works? So it's the same p-value idea. Okay, how do you think we're going to find the p-value? Yeah, we're going to go to the calculator. So let's go back to the calculator. That was, there we go. And I tried to make it obvious. Which calculator number do you think we're going to use? Definitely not a trick question. Yeah, this is calculator number 21, goodness of fit. And what it says is type in the values from the observed and expected sets separated by commas, then hit calculate. So let's do that. And I think it's easiest to just copy, paste, and put commas in. And then copy the second one. Paste that guy. And put commas in that one. Any questions on entering in the calculator? Then hit calculate. Okay, notice the chi-squared is 18.35. That's a test statistic. So if you're asked to find the test statistic, then you write chi-squared equals 18.35-ish. The p-value is 0.00037-ish. Any questions on that? Okay. And here's the picture, by the way. There's your chi-square distribution with that many degrees of freedom. Okay. And it actually shows you the different level of significances. And the p-value is very, very far to the right, way over here. Yeah. So that means probable isn't the word we use. What word do we use when the p-value is really low? What two words specifically? Not probable. Yeah, statistically significant. Okay, again, that nothing's changed in terms of hypothesis testing. It's the same technique, same step by step that we've done before for hypothesis testing. Okay, the only new thing is now we can handle survey questions where the survey question is a quantitative, not yes, no question. What is your race in this case? Any questions on that? So 00037. So chi-squared was 18 point something. 0.35. And the p-value was 0.00037. Any questions on that? All right, so now we can state our conclusion. It's very similar to what we've done before. What do you think the first, bunch of words are? Yeah, nothing's changed. That's a hint in terms of what we've done in the past. For the beginning. The end changes a bit, but not the beginning. So what are the first few words? Yeah, there is statistically. By the way, it's not a 95% level of significance. You would never use a 95% level of significance. Just note that. All right. In our class, we use 5%, 1%, or 10% level of significance. 95 was for confidence levels. So that's real important to note. Okay, there is statistically significant evidence. And if you want, because the p-value is less than 0.01, you can say there's strong. Not strong, statistically significant evidence to conclude that, and the good news is I've already typed out what I'm concluding. I just copy and paste H1. Maybe change the format a bit when I'm done. So not capital T. The distribution of races at California Community Colleges is not the same as the distribution of races in California. Any questions at all? Any questions on the conclusion? By the way, just want to let you know, when you find statistically significant evidence, do not use whether or not. That was a mistake a couple, one or two used on the exam. So I just want to note, whether or not should never happen when there's statistically significant evidence. That can only happen when there's insufficient or statistically insignificant evidence. Okay, so that's just I figured I should note that because I noticed that when I was grading the exams. So there's strong statistically significant evidence to conclude that the distribution of races at California community colleges is not the same as the distribution of races in California. Can we say that, hey, we observed more Latinos than we expected, so the reason why the distribution of races at California Community College is not the same as the distribution of races in California is because there's more Latinos? Okay, and the answer is you can't conclude that from this p-value. And this is maybe the first time I'm going to say this, but for the rest of this course, I'm going to say this a lot. So do you think it can be, you can decide whether, which is the one where it's off? Yeah, and if you want to find out, do you know what you need to do? And again, this is the first time in this course I'm going to say it, I'm going to say it a lot. No, not another sample, it turns out. Not quite 8 years of calculus. That's if you want to understand the mathematics behind the goodness fit test. No, so you need to take an upper division statistics class or a master's level statistics class, but upper division is usually enough. And then there's another statistical test to actually decide which is the one. Okay, but we can only do so much in our class. But I want to give you a heads up that just because we don't do it doesn't mean it can't be done. It just means that we only have so much time in our class. Okay, so it's not done in the elementary stats class, pretty much in any college, but it is done in upper division stats classes. Yeah, so not a whole 8 years of calculus. 8 years of calculus is if you want to fully understand the chi-squared mathematics. So that's a whole different thing. Okay. Any questions on this goodness of fit test? Any questions? What do you think the hardest part is? And my definition of hard, by the way, means students get it wrong on the exam. What do you think the hardest part is for the goodness of fit test? Writing the conclusion, that's a little bit difficult. Forgetting distribution, no, that's not the hardest either. Because those who pay attention don't. Those who don't watch the webinar don't. They forget. Should I tell you? Knowing to use goodness of fit test. That's the hardest part. The very, very, very start. And that is which test to use. So the bad news for you is that we're going to have 3 different tests for the chapter 11. And they all sound somewhat similar. They're different, but they have some similarities, and people confuse one to another. So that's one of the hard parts. So I want to let you know that you use a goodness of fit test when you have a known distributions population with a known distribution. You have another population with an unknown distribution, and you want to see if the unknown distribution is the same as the known distribution. See how it works? Okay, so it's not just because it's a qualitative not yes, no question. Yeah, so so this discussion, you're going to post, by the way, you're going to post an article from, and the best, maybe I'll show you just in case you don't know how this is what you should do. It's a whole lot easier is go to Lake Tahoe Community College. Scroll to the bottom, go to library, go to find articles, and then academic search complete. And then type in something you want. And usually within 4 or 5 times, you're going to find something that uses a chi-square test. And so you're going to post something that uses the chi-square test. Often they don't say which test they use, but you're going to have to identify it when you reply to someone else's post. Okay, sometimes they just say chi-squared because everyone's supposed to know. You know how things are. Does that make sense? Does that answer your question? Okay. Yeah, and again, this EBSCOhost search, it really is the best way of finding these kind of things. It's much faster than trying to do it individually because you're going to have to do something that is, published and peer-reviewed. And these guys are peer-reviewed articles. Yeah, so do your best. Do your best. Sometimes it takes 4 or 5 tries. But as I mentioned in the instructions, you can't have the word chi-squared or good as a fit or any of those in the title of the article. So be careful about searching for chi-squared because then you're going to have something about chi-squared. So that's just a note. But chi-squared is so common that it's not that hard to go look for. They sometimes will say which type of test. Sometimes they just say the chi-squared value was. Does that make sense? If they say the chi-squared value was, that means they used a chi-squared test on one of the three that we're doing. And I do recommend identifying, before you post, make sure you understand what it is. If you have no idea how to answer it, then it may not be a good thing to post, or it might be too hard, you know what I mean? And also it means that you need to do a little more research on the different tests. So here's the second type of test. Okay. So here's a question. Does it matter what season a person was born when it comes to the type of car they drive? What do you think? I was born in the summer. Do you think that's going to help you understand what kind of car I drive? What do you think? Okay. So, right. Some of you might think it will. Some of you might think it won't. All depends on whether you believe in astrology. Hopefully you know what astrology is, right? Kind of when you were born, and then your whole personality is affected by that. That's astrology. And just like me, I don't believe in astrology at all. Okay, but you do. So you might think that this is a yes. I did make up these numbers, but this is a survey that could be done. It would not be a hard survey to do. Okay. Table below shows the season and the car type. And we have spring, summer, winter, and fall. Those are the 4 seasons. And we have sedan, SUV, and other. Sound good? All right. How is this one different than the last one we did? Why can't we use goodness of fit? Yeah, actually, it's only 2 variables. Variable 1 is season, variable 2 is kind of car. Yeah, we're not comparing distributions. That's the difference, right? We're not looking to see if the distribution of something is the same as something else. What we're looking at here is the season someone was born in independent of the kind of car they drive? Any questions on that idea? Or is it dependent on the kind of car they drive? Is that clear that that's what this is asking? Because that's what dependent means. Dependent means that if you're told the answer to one question, that will change the probability of the different answers for the other question. So if you're told the answer to when they were born, summer, then that would change the probability of sedan, SUV, and other. And that would make it dependent if that was true. Any questions on that idea? All right, so we're going to be using the chi-squared test for independence. Any questions on that idea? All right, and we use it when we have 2 survey questions that are both qualitative, and we want to see if they're independent or dependent. Any questions so far? All right, once I've decided on this test that I'm going to use, what's the next step? You should be used to this. Yeah, not the calculator yet, the hypothesis test. We want to decide H0 and H1, right? You always do that before the calculator. Is that clear? So here's H0, and that is the season a person was born in, and the person's car type are independent. And H1 is the season a person was born in, and the person's car type are dependent. So I do want to note, which I always do when I do it, and that is I have highlighted in red the word independent for H0, the word dependent for H1. Don't get it mixed up. And those words have to be there. Got it? Any questions on that? Okay, so it's always the answer to the first question and the answer to the second question are independent for H naught and are dependent for H1. Is that clear? Okay, and notice for typing, by the way, you can just like copy that guy and paste it right here because nothing changes except that you could copy it all and just erase the IN. A lot less typing. Just let you know that H naught and H1 are very similar in, the letters that you use. The only difference is this one has an IN because it's independent. This one doesn't because it's dependent. Any questions at all on this particular example and this H naught and H1 and why this is a chi-square test for independence? All right, what do you think the next step is? We should be used to this. Yeah, now we go to the calculator. Okay, can we use this calculator? One we just used? Yeah, don't even think about it. It's not as good as a fit test. So I can go back to the calculator menu. And what calculator number do we use? This should be obvious. Yeah, 22. It's a test for independence. And then it says, enter the observed values, hit calculate, and the chi-squared test statistic and the p-value would be calculated for you. Leave blank the last rows and columns that don't have data values. I want to let you know a kind of really nice mathematics that happens with this that makes life a lot easier for you. And that is, it turns out, it doesn't matter whether you write columns or rows. You get the same answer. So whatever's easier to type is what you should do. So you'll notice that in my table, we have the 73, 81, 76, and 78 as the first row. It could be the first column. It really doesn't matter as long as you're consistent. Is that clear? And in particular, there's 4 columns, so we can actually fit them. But if there were 6 columns, you can actually just make them rows instead. So that's why I have a whole lot of rows and not so many columns, because that gives you good opportunity. So now I got to type them in. 73, 81. $76, $78. And then the next row is 65, 68. And then 62, 64. And then the third row was 43, 51. And 48, 50. Any questions on entering the data? So what if both have more than 6? Okay, so here's the deal, the bad news. There's bad news and good news. The bad news is you can't use this calculator. And you know what the good news is? Any guess? Yeah, a different calculator in particular, if you want to, are the spreadsheet calculator that we used. The spreadsheet calculator that we use has a tab for chi-squared. And that one could handle as many rows and columns basically as you want. Okay, that won't happen on any exam question or homework question, but in the real world, if you needed it, you could always do that. Okay, yeah, the Google spreadsheet calculator I made, yeah, that did have a chi-squared. That's more like after this course, because this course I don't have anything, there's no reason to torture you by, having to type in, 200 numbers. So that's why I don't do that. Not because it never happens in the real world, just because I only do so much. Okay. Where can you find the one I made? So that's the where you use the projects. So let me remind you. It looks like this. Do you remember that one? This is what you use for project 1 and project 2 you're going to use also. And then you'll notice there is a chi-squared. And it has first, second, third, etc. A, B, C, D, F, G, H, it just keeps going. And you can go all the way down to. That's how spreadsheets work. Okay. If you have too many, then you pay someone else to do it. Who would want to do it? Sounds like a waste. Okay, so anyway, let me get back to the calculator. So I'm going to scroll down and hit calculate. Okay, so here we have chi-squared is 0.48 about, and our p-value is 0.998. Okay. So 0.48. And then p-value is 0.998. Any questions on that? I do want to let you know something, that I got an email actually, I think 2 days ago, that there was an error in that chi-squared calculator's picture. Because remember, those pictures are new. I made those in December. And I fixed the error. And my guess is it wasn't from anyone in our class, probably not even from someone from Tahoe. But if you ever find an error, please let me know, and then I can go fix it. That's the good news. I'm the author, so I can actually fix it. Especially in the pictures, because those are brand new, so not a lot. So people haven't looked and told me about errors yet. Nobody's perfect. Okay, so do we accept the null hypothesis? Never. Never. You never accept the null hypothesis. Okay. In this case, we're going to fail to reject the null hypothesis. Our p-value is large, but the p-value is so large, you would fail to reject and give up. You wouldn't say, well, maybe if I just got a bigger sample size. You would look at this and say, oh, yeah, no, I think I'm giving up on this one. Does that make sense? There's a good chance that H naught is correct, but you can't know for sure. Okay. So what we can do is we can say there is statistically insignificant evidence to make a conclusion. That, and again, I can just copy and paste H1. And make the not capital. Just to make it prettier. Oops, missed. Try it one more time. The season a person was born in and the person's car type are dependent, right? And the key word, it's very important, is insignificant in this case. Any questions on this example? Okay. As I mentioned, it turns out that both examples we've done use this chi-squared distribution. Okay. You probably don't even notice it when you're using the calculator, but you know, the math that's kind of behind the scenes is using this chi-squared. Ready for another example? Okay, so the example is, do single men and women take the same type of vacation? Table below shows the results of the study. What do you think? Right? Do you think single men and women take the same kind of vacation, or do you think they have a different type? Instead of type, what word might we use? Yeah, distribution. Okay. So this is looking a little like goodness of fit, but how is it different? This is not goodness of fit, but why is it not goodness of fit? What's different from this for this versus the original goodness of fit question? Yeah, we don't know either population distribution. That's the big deal. Okay. It's not that it's a comparison study, because we were doing a comparison study for the first example too. We were looking at California community college students versus Californians. That's a comparison study. But this example is also a comparison study, but the difference is that here we don't know the population distribution for males. We don't know the population distribution for females. Is that clear? So the name for the test we're going to use is called the chi-squared test for homogeneity. Okay. When you think of the word homogeneous, what do you think of? You might have heard it from homogenized milk, by the way. Yeah, it's the same distribution in this case. Yeah, that's what homogeneous means. It's the same kind of ingredients or distribution. Okay, so that's what chi-squared homogeneity is all about. I will tell you kind of a fun little thing, and that is, I don't know if I've told you, but I've done a lot of statistical consulting. People will ask me for help in some research project they're doing, and sometimes it's a business, and then it turns out I don't charge them money. I don't take money from people to do statistical consulting. But if it's a business, I do ask for money, but in a different way. Any guess? So just in case, so maybe 5 years from now, and you know, you got your own business and you need some statistical help, and you ask me, I'm going to ask you not to give me money, but I'm going to ask you to donate to a scholarship at our college. Sound good? And there's been thousands of dollars donated for scholarships at our college because of statistical consulting that I've done. So let you know that I've done some of this kind of statistical consulting. And what I found is that homogeneity is one of the main tests that's used. Okay, when I have to, you know, help others out. By the way, if you're a student, let's say at a university, and you need my help, maybe to get a master's degree, then I don't even ask for money. I'm just happy to help you. The one thing I will ask, though, is I want to read your dissertation when it's done, or your thesis. So please email me your thesis so I can read it, and that makes me smile. That's all I want. Okay, but I'll definitely help you with statistics even after you're out of the community college system and then moved on to the university system to get a, you know, bachelor's or master's or PhD, whatever you're getting. So just let you know that that's kind of what I do. Okay. So the question is, let's go back to this. We have a chi-squared homogeneity, so we need H1 and H naught and H1. So H naught is the distributions of travel type are the same for men and women. H1 is the distributions of travel type are not the same for men and women. By the way, I've highlighted, how does this differ from good as a fit? How is the highlighted word different? That's something I mentioned when someone guessed it, when typed it wrong. Yeah, it has an S at the end. We're talking about two different distributions. We don't know either of them, so we're going to use distributions. Does that make sense? We don't have a distribution is the same as and we don't have an unknown is the same as a known. We have two distributions are the same as each other, and we don't know either of them. Is that clear? Okay, so we need a chi-squared and a p-value. What do you think we're going to do next? You all better tell me. Y'all should know. Yeah, go to the calculator. So let's go to the calculator. Can I use a chi-squared test for independence calculator? Yeah, that's not going to work. So now, okay, I'm going to go back to the calculator menu. And by the way, I was doing all this consulting and I realized that homogeneity was just happening over and over and over and over again. And it's like not that much, it's no harder than the others. So I actually emailed the author of the textbook I was using, which is the same book, the OpenStax book. And I asked, can you, in the next edition, can you put homogeneity in it? And do you know what she told me? Any guess? Kind of. Instead of saying, yes, I'll put it in, she says, we can put it in, but can you write it? And can you put it in? So I actually wrote that part of the book. It's like a couple pages. So that was, a piece that I wrote because, she agreed that it was really important. So just let you know that it is really important and it's now in the standard book. Okay, what test are we using? What number? What calculator? Yeah, this is 23. I want to let you know something. How many are left? No, I'm not the only person that could do homogeneity. I just noted to the author of the book that that's something they want to have. There are a whole lot of other tests too that we don't cover in this class, but homogeneity was just so important it needed to be covered. Yeah. You'll notice that there's only 2 tests left. How many weeks left in the class after this week? Not counting finals. Not 1. Not 3. It's pretty funny. 2. Yeah, yeah. We're in week 9. There's week 10, week 11, and 12 is finals week. So there's only 2 weeks left. And yeah, that's why there are 2 calculators left. One for next week and one for the week after. So we're almost at the end. The light is definitely at the end of the tunnel. So I'm going to click on the test for homogeneity. And it says enter the observed values for each of the 2 samples, A and B. So notice you don't have observed and expected. Now it's observed and observed. There's nothing expected. And the chi-squared test, there isn't a chapter for the last week. Yeah, no, the last week there's very little to do. You have your final exam, which isn't even that big. So the last week is maybe the easiest week of the class because we're supposed to be done halfway through. Is the idea. So yeah, so there's not much on the last week. Okay, so for A and B, and I put these as columns just because it fits better on a phone or on a computer, whatever. It just looks a little better, especially on a smartphone. So that's why I made them columns. And we go ahead and put the numbers in. 29, 47, 33. $29, 47, 33. And then the second column should be the second row, 38, 42, 36. Remembered it right. 38, 42, 36. Yeah. Just scroll down and hit calculate. Any questions? Any questions? Okay, what do you notice? Yeah, the test statistic, and in particular, the p-value is about 0.4956. Chi-squared is about 1.4. And 4956. All right, what's the conclusion? The p-value is high. What's the conclusion? At least the first two words. Hopefully you're getting convinced that what we did a couple weeks ago keeps happening. So it is really important. And that is hypothesis testing. Yeah, you failed to reject the null hypothesis, so there is statistically insignificant evidence to conclude that, and now I can just copy and paste H1. Make that T lowercase, that the distributions of travel type are not the same for men and women. Okay, does that mean men and women travel in the same way? What do you think? Yeah, we can't say that. All we can say is we don't know anything. It's just a very fancy way of saying we don't know anything. Okay, it could be that our sample size is just too small. It could be that they travel in the same way. We really don't know when you have statistically insignificant evidence. Any questions on that? Okay, so now you might be able to see my shirt, but you probably can't. Right here. What's the big thing happening today in America? Yeah, this is it's called Super Tuesday. Have you heard of that? And again, if you look, doesn't show very well. Maybe I need to like make it darker or something. Says I voted. I voted today. Okay, and voting's important, by the way. Okay, so if you are eligible to vote, you should vote. I can't say that enough. Let me just put this way: is that my first election that I ran, there were, it's not a huge city. It was 20,000 votes or so, and something like that. And I only won by 3 votes. I don't see Trump on there. You mean on your ballot? When you say on there, I don't know what you mean by on there. Okay, so this is a primary election. So that if you don't see Trump, that probably means you're not Republican. By the way, I didn't see Trump either, because I'm not Republican either. Okay. If you are Republican and don't see Trump, then you should worry, because the Supreme Court said that that has to happen. But he's not on my ballot either. Just let you know that. So yeah, this is the primary election. If Trump wins a primary, which it's looking like there's a high probability he will, then you should see Trump on the November election ballot. Okay, that's kind of how elections work. It's one of the things I know well about, because I was actually, like I said, I ran for elections twice and won. But, so that's why. But here's what we can do. Okay, a study was done asking 100 people who voted how many minutes they spent researching the candidates and the proposition. Okay. The mean was found to be 22 minutes and the standard deviation 8 minutes. Okay. Can bipartisan voters vote on the primary ballot? Yeah, I don't know exactly what happens for that, but if you don't have a party, sorry if I'm not an expert on that part. But you definitely can vote because at least in California, there is actually one item in California's ballot that's not a person. It's a you know, something. It was something about mental health facilities, if I remember right. Again, what I won't tell you is what to vote for, but I will tell you that if you are, you know, eligible to vote, you should vote. That'll tell you. Okay. All right. So the mean was found to be 22 minutes and the standard deviation was 8 minutes. The table shows the results. Is the distribution normal? Okay. Okay, not the distribution, not the sampling distribution. This would be the distribution of the population. Is that a normal distribution? And we've heard that a lot where you have to assume a normal distribution, right? Remember that? So it turns out this is, you know, this is really the first time, and there's other tests to look at normality also, but this is the first one and the only one. There's others. By the way, what are you going to have to do if you want to learn about other tests to find out if you have a normal distribution? Any guess? They run samples. No, that's for the sampling distribution. This is the distribution of the population. That's different. So let me tell you, it's what I had said a little earlier. You have to take an advanced statistics test. That's what you have to do. So advanced statistics class. So you have to go to a university and you have to take an upper division or graduate level stats class. And you'll learn about the Kolmogorov-Sky test for normality. I'm not going into that one. We're going to go into the chi-square test for normality, as we'll see. So the table shows results. So there were 20 people. There were 20 people that said they spent less than 14 minutes in researching candidates. There were 73 people that said they spent between 14 and 30 minutes researching the candidates. Okay. And by the way, in case you don't know, it's not just presidential. There's multiple candidates for multiple things. There's Senate, and then there's a state assembly. So, you know, all the different candidates you have to research. Okay. And then 7 people spent over a half an hour researching candidates. Any questions on that? All right. Let me ask you something. What's important about the numbers 14 and 30? Those are not just general random numbers. Those are important numbers. What's important? What do you notice? Divisions of an hour? 14 isn't a special division of an hour, that's for sure. 14 over 60 is not some pretty number. Okay, if you don't notice, let me tell you. So the mean was 22. The standard deviation was 8. So the z-score for 14 would be 14 minus 22 divided by 8. 14 minus 22 is negative 8 over 8 is negative 1. The z-score for 30 is 30 minus 22, which is 8 divided by 8, which is 1. So saying that x is between 14 and 30 is the same as saying it's within 1 standard deviation of the mean. Any questions on that? Okay, expected means that if it is a normal distribution, then we would expect it to have what percent within one standard deviation of the mean? Do you remember the empirical rule? If it's a normal distribution, what percent should be within one standard deviation of a mean? And you remember? I know it's been a while. It happened though. Yeah, 68%. So that would mean that our expected would be 68%. Now, 68, I tried to make this easy, by the way. I did make up these numbers, by the way. So, it's not like I really did a survey, but you can imagine it. What is 68% of 100 people? I hope you don't need a calculator for that. 68, yeah. Okay, so that would be 0.68 times 100. Yeah, not supposed to be tricky. Okay, and then we have the other two sides. I think the easiest way of looking at the other two sides is if there were 68 that were within one standard deviation, then there were 100 minus 68, which is 32, that are outside one standard deviation. And then it is even on both sides, so half of 32 is 16. So that's going to be 16. And 16 on the left, 16 on the right. Any questions on that? Any questions? What test are we using? What kind of hypothesis test are we working on here? And we've already dealt with it. We've done the 3. It's one of the 3. Yeah, this is a goodness of fit test because we want to find out if the distribution of the sample is equal to a known distribution called the normal distribution. Do you see how that works? And if there's an unknown or a sample, and you want to compare it with a population that you do know, in this case, normal, we know exactly how normal distribution behaves, then we use goodness of fit test. So the test to use is goodness of fit. Any questions on that? Then we have H naught and H1. H naught is a distribution of voter research time is normal. Is that clear? Okay, notice the survey question is a quantitative question. The survey question is, how many minutes did you spend researching the candidates before you cast your ballot? Right? And that is very quantitative, But what we've done is we've really broken up into 3 pieces. We have the left tail, we have the middle, and we have the right tail. So we've taken something quantitative and turned it into something qualitative. Any questions on that idea? All right, so then we go to the calculator. Let's go back to the menu. And we already said it was the goodness of fit test, so it's 21. And the observed values were 20, 73, and 7. The expected values were 16, 68, and 16. Any questions at all on performing this test so far? Any questions? I do want to give you a heads up. It's always easier to watch me do it than do it yourself. So, practicing, you might need some help, go to a tutor and all that when you're, working on this stuff because watching is not the same as doing. So I hit calculate. And there we go. We have a chi-squared is 6.43 about. We have a p-value of 0.04. So let's write that out. 6.43. By the way, what level of significance do you think we should use? Yeah, this is politics. I mentioned politics always uses 5%. I don't think I've ever seen any politics study ever use anything other than 5%. So we're going to use a 5% level of significance. Our p-value is 0.04. So what's the conclusion? Yeah, it is statistically significant because p is less than alpha. 0.04 is less than 0.05. So we can say there is statistically significant evidence. By the way, you should not say there's strong statistically significant evidence because it's 0.04 and that's not quite small enough for strong. But you can say there's statistically significant evidence to conclude that, and I just take H1, I copy it, and I paste it, and make the lowercase, that the distribution of voter research time is not normal. Any questions on that? So this is the first time in our course where we've actually, instead of just like assuming it was normal, we're using the central limit theorem so we don't care. We actually now can test it to see if it's normal. Do you see that? We did before kind of visually look at it and say, yeah, does it kind of look bell-shaped? What's the problem with it kind of looks bell-shaped? What's the problem with that statement? Yeah, it's highly inaccurate. It could be biased. It's like how you feel that day in terms of how close to Bill you want it to be. Does that make sense? So it's not scientific at all to just look at it, look at the graph and say, yeah, kind of looks bell-shaped. That's good enough for me. Instead, what you do is you do a statistical test. And again, as I mentioned, there's more than one statistical test to decide whether you have a normal distribution, but I'm showing you this one, okay, which is the goodness of fit test. Okay. You could even get more granular if you really wanted, and you can say, well, instead of just less than 14, you could say, well, what about between 6 and 14, 1 and 2 standard deviations? And instead of greater than 30, you could say, well, how about 30 to 38? Because that's 1 and 2 standard deviations. I mean, you could go further if you want, but I'm keeping it simple. This is elementary statistics, so keeping it a bit simple. Okay, but this at least shows a little bit of science behind saying that it is statistically significant evidence to conclude that the distribution of voter research time is not normal. Any questions? Any questions at all on any of the chi-squared tests? Any questions? All right, I did promise that this is going to be a little bit shorter than usual. Chi-squared is usually not the chapter that everyone complains about, but I do want you, what else should you be spending a lot of time on this week? Yeah, project 2. So I do lighten up a bit now because it's time to work on project 2. Okay, so project 2 is important, and make sure that don't wait until next week to get it started. It's an easier chapter, so you should have a little more time, as a group to get project 2 worked on. And I'll be happy to check. In fact, I have a little more time than I usually have. Any guess on why? I know there's a few of you that should know. I know at least one of you. Yeah, campus has been closed. I don't know who's from Tahoe in this group, but so I had more time because I was sitting at home all day. I had a lot of shoveling of snow to do because, you know, if you're in Tahoe, you understand. But other than that, I was able to get more done. Okay, so you know, I was able to grade all your stuff a little earlier than usual, but I'll be happy to, you know, take a look at anything and talk to you about anything about the projects. So what I want to do is give you the secret word, and that is known, K-N-O-W-N, because if you're looking at the goodness of fit test, you want to see if the unknown distribution is the same as the known distribution. I always try and use a word that you wouldn't guess after reading the chapter, but explaining it now, that makes some sense probably, right? So that's the secret word for this week. Do not forget to type that in. This is not supposed to be some trick question. You just type it into the secret word quiz, and then you're done. And then you get full credit. Okay. So there was a question, what should we do after collecting the data? Start writing your project. Start writing the project. And as I mentioned when I went over the project, there's an order at which you write it, right? You start out with your null and alternative hypothesis and maybe a paragraph at the beginning to explain, you know, what the project's about, just an introduction. Then you do the null and alternative hypotheses. Then you write down the ramifications of a type 1 and type 2 error. Then after that, you write down what your level of significance is based on those ramifications. And I do want to mention something because a lot of people made the mistake. Most of you made this mistake. When I asked you for the ramifications of a type 1 and type 2 error on the exam, a lot of you did not give me the ramifications. You gave me the definition. So, for example, in the voter research one that we just did, the ramifications of a type 1 error is not that we reject the null hypothesis and decide that the voter research time is not normal when it really was normal. That's not the ramifications. That's the definition. The ramifications is what disaster or terrible things happen because of that. Is that clear? That's the ramifications, not that you rejected the null hypothesis and the null hypothesis was true. That's the definition. Is that clear? Okay, so after going over H0 and H1, you do the ramifications of a type 1 and type 2 error. Okay, you can include the definition, but most of the writing should be about the ramifications. The definition is just a quick sentence, but if you should write down the ramifications because based on the ramifications, the next step is deciding the level of significance. Then after you have level of significance, then you write about the statistics that came in. So that'll be your lower bound for the confidence level interval, the upper bound for the confidence interval. Okay. And you could choose whether to do confidence interval before hypothesis test or hypothesis test before confidence interval. Don't put those two things in the same paragraph, though. They're a huge part of the project, and they should be separated. Do not say that you used a 95% confidence level because you used a 5% level of significance. You do not have to have those match. For the confidence interval and the confidence level, you can look at the intervals for 95%, 99%, and 90%, state the pros and cons of each, and then state based on your client's needs, which one serves the client's needs best. That's how you decide on whether it's going to be 90%, 95, or 99%. Okay? So then you write that, and then once you have talked about that, then you talk about the lower bound for the confidence interval, what decisions the client will make based on the lower bound, Then you talk about the upper bound for the confidence interval. What decisions will the client make based on the upper bound? Because that's what a confidence interval is. It's a lower bound and an upper bound. Okay. Then, once you've done that, then say that if you wanted to satisfy your client's needs better, and let's say you wanted to use a 99% level, but not change the margin of error, how much larger a sample would you need? A little bit of basic math to do for that, but that's what you're gonna have to do. And that's so you can decrease the standard error. Okay, so that's where you bring the standard error into it at that point. Then what you can do is write down the p-value. Now, after that, then you're going to be talking about the hypothesis test. Write the conclusion of the hypothesis test, write it in a paragraph, not just a templated sentence. You should be writing what the conclusion is and what decisions the client will make based on it. Does that make sense? Similarly, you should look at the p-value and what decisions the client will make based on the p-value. Okay? Talk about the level of significance. Don't just use a template. Template is to write short. This is to write, projects are longer. Okay? Then, after you're done talking about those three things, then decide, was your standard error small enough? And that should be based on your conclusion and your p-value. Okay, then you could look at the standard error again and just decide, what does the standard error tell you? Do you have pretty reliable data based on the standard error? Okay. Then after that, you might want to, then you write kind of a conclusion. You may also want to talk about what your sampling was, just quickly. And if you were to do another study, what other things might you do? Any questions on, does that help? You're asking what you should do. Those are the steps to the project. Don't miss any of them. And remember, this is recorded, so you can always go back and listen again. So you know what to do. Okay, and then after that, what do you do after you finish writing all that stuff? Yeah, email it to me. And actually, the thing I recommend doing is having a meeting with your partners and read it, together and make sure you're all happy with it, and then email it to me. Sound good? It's always good to have conversation with your partners. Okay, and then email it to me, and then I will email you back, just like I did with Project One, if you emailed me in time. And I'll email you back a list of suggestions to improve. And I always give you suggestions to improve. I don't talk about the things that were fine. I talk about things that need to be changed. Just let you know that. So just because I give you a long list does not mean it's a terrible project. It just means that there are a lot of things that could be changed. Okay. And then once you've read my list, what do you do next? You fix it. Yeah, you fix it. So you address all the things I did, and you can talk to a tutor, you can come to my office hours, whatever. You can't send me a draft a second time. I only read one draft. Otherwise, you can keep sending me draft. I can't do that. So I read one draft, and then after you've gotten back together with your partner and said, yeah, we're happy, then you submit it on to Canvas. Sound good? Okay. And then after, and then the following week, maybe, Monday or Tuesday or Wednesday, then you look at Canvas and look at your grade. I don't take forever, but Monday's usually a pretty busy day, so probably on that Tuesday is when I'll have it graded. All right, I think I'm going to call it. So I'm going to stop the recording.